Hello everyone. So today we're going to go over section 10.2, logarithmic functions and their transformations. Suppose we sketch the graph of y equals 2 to the x power and use a table of values. So when x is equal to -3, for example, we'll have 1 over 8. When x is equal to -2, we will have 1/4, followed by 1/2, 1, and of course then 2, 4, 8, and finally 16. And here we can plot the points onto our grid. And we'll have a graph that looks like this. So next, we can consider the inverse of this function. That, of course, will be x equals to 2 to the y power. Okay, so when x is equal to 1 over 8, y is equal to -3. When x is equal to 1/4, we have -2. Then 1/2, 1, 2, 4, 8, and 16 once again. And we know that the graph will be reflected over the line y equals x. So let's draw that in first. So the points 1, 0, 2, 1, 4, 2, and then 8, 3. And then we also have 1/2 -1, 1/4 -2, and so forth. So what we have here is a case where we can rewrite x equals 2 to the y power, which of course is in exponential form, into logarithmic form. And we'll have y is equal to log base 2 of x. And the idea here is that the exponential function and the logarithmic function of the same base are inverses of one another. Also of note, of course, are the asymptotes of the two graphs. The function y is equal to log base 2 of x has an asymptote at x equals 0, just as the function y equals 2 to the x has an asymptote at y equals 0. Just going to go ahead and draw those in as well. Once again, a logarithmic function is the inverse of an exponential function of the same base. So the original function could be f of x is equal to sum a to the x, and its inverse would be log base a of x. Okay, so of course, since the two functions are related in that way, in that they're inverse of one another, we can look at their properties as well. So we're going to have the function y equals 3 to the x, and of course the domain x is an element of the real numbers, range y is greater than 0, there will be no x-intercepts, the y-intercept is just 1, and it has an asymptote at y equals 0. Okay. The associated logarithmic function, that is y equals log base 3 of x, will have the domain x is greater than 0, the range y is an element of the real numbers, the x-intercept would be 1, it will have no y-intercepts, and the asymptote is x equals 0. Okay. So also of note, considering what we know about the graph of y equals 1/3 to the x power, which of course we know is the same as y equals to 3 to the negative x, which is reflection of y equals 3 to the x over the y-axis. So once again, that is, we start with y equals 1/3 to the x, which is equal to y equals 3 to the negative x, and that's a reflection of y equals 3 to the positive x over the y-axis. So using that line of thinking, then y equals to log base 1/3 of x would be the reflection of y equals log base 3 of x over the x-axis. Okay, so that was an introduction to the idea of the logarithmic function. Now we're going to move on to some transformations. Okay, so here we are going to start with just y equals log base 3 of x, and then we're going to graph y equals log base 3 and then x plus 9 in parentheses and then plus 2 afterwards. So one way to look at this is to consider the transformations, of course. This would be left 9 spaces and then up 2 spaces. Okay. And to start with, we're going to graph y equals to log base 3 of x, which of course we know we can graph using the exponential form. X is equal to 3 to the y. So then we can have a table of values. 1/3, -1 is one of the points. 1, 0 is the second point. 3, 1 is the third point. And 9, 2 is our fourth point. So let's see here. 1, 0, 3, 1, 9, 2, and 1/3, -1. And of course, we can also add in 1 over 9, -2. So now we can go ahead and draw a sketch of this graph. something like this. And of course, we can add in an asymptote at x equals 0. Okay. So if the graph is to be moved 9 spaces to the left and 2 spaces up, we're going to take the x values and subtract 9 from each one, and take the y values and add 2 to each one. So then we have, instead of 1/3, -8 and 2/3. Instead of 1, we'll have -8. Instead of 3, we'll have -6. Instead of 9, we'll have 0. And here we're going to take each y value and add 2, so we have 1, 2, 3, and 4. And we can go ahead and plot those points. So let's start with -8, 2, -6, 3, and of course 0, 4. And finally, -8 and 2/3, 1, so somewhere around here. We can add an additional point as well. And draw a sketch of this graph. So one thing we will notice immediately is that these two graphs have the same shape. That is to be expected, and that the graph indeed did move 9 spaces to the left. You can see that the asymptote also moved 9 spaces to the left and 2 spaces up. So this asymptote will be x equal to -9. And of course we can add that to this small table of properties that we have. X equals to -9 is the asymptote, so the domain is x is greater than -9, and the range, y, is an element of the real numbers. Okay, so next question asks for the x and y intercepts of the function, which we can find algebraically. So let's start with the x-intercept. So to find the x-intercept of a function, we let y equal 0 and solve for x. So we have 0 is equal to log base 3 of x plus 9 and then plus 2. Okay. In other words, we have -2 is equal to log base 3 of x plus 9. This can be written, of course, in exponential form, so 3 to the -2 power is equal to x plus 9. So x is going to be equal to -9 plus 3 to the -2 power, which we know is the same as -9 plus 1/9, and we'll get -8 and 8/9, which agrees with our graph at this point here. So we know that is a good answer. Now for the y-intercept, we let x equal 0 and solve for y, of course. So go ahead and do this over here, y-intercept. So we have y equals to log base 3 of 0 plus 9 plus 2. That, of course, simplifies to just y equals to log base 3 of 9 plus 2, which is quite fortunate because 9 is a power of 3, so that logarithm can be evaluated directly, so that gives us 2 plus 2, which is 4. And we can see here we do have the point 0, 4 on our graph. So that's our y-intercept. Okay, so that's the idea for graphing these logarithmic functions. Let's move on to example 2. This time the base is 2, so we're going to start with y equals log base 2 of x. Okay, and of course it is related to the function, or the inverse of the exponential function, so we can write it as x is equal to 2 to the y power. And then we're going to make a table of values, so 1/2, 1, negative 1, 1, 0, 2, 1, and 4, 2 are the points. Let's go ahead and plot those. And of course, we can also add in points like 8, 3, 1/4, negative 2, even 1/8, negative 3. So a graph that looks like this. And now in the second step, we're going to consider the transformation that has occurred. Okay. So let's look at the equation here. And we can see that we can factor the 2. So we have negative log base 2, and then 2, and finally x plus 3. Sorry about that. So the 3 transformations are reflection over the x-axis, followed by a horizontal stretch by 1/2, and finally the 3 moves the graph left 3 spaces. Okay. So we're simply going to take our table of values from before and transform the numbers that way. So reflect over the x-axis, so that would just mean that our y values will become their negative equivalent. So instead of negative 1, we'll have positive 1, and then 0, negative 1, and negative 2. Okay, the x values, because of the horizontal stretch by 1/2, will be halved and then move left 3 spaces, so subtract 3. So 1/2 half is 1/4, minus 3 gives us negative 2 3/4. 1/2 is just a half. 1/2 minus 3 is negative 2 1/2. 2/2 is 1. 1 minus 3 is negative 2. 4/2 is 2. 2 minus 3 is negative 1. So these are our 4 new points. We have negative 2 3/4, 1. So it'll be around here. Negative 2 1/2, 0. Negative 2, negative 1. And finally, negative 1, negative 2. So these are our 4 points that we can use. Okay. So the graph will look something like this. Okay, so again, just as before, we have our asymptotes for the original function. We have our asymptote at x equals 0. And for the transform function, we will have the asymptote at negative 3. this is x equals 0. And next to that, we have x equals to negative 3. Okay, so now we can once again consider the asymptote, which we just found already. So that would be x equals to negative 3. The domain then is x is greater than negative 3. And the range of this graph, y is an element of the real numbers. Okay. Also, just like the previous example, we're also going to look for the x and y intercepts. Okay, so let's start with the x-intercept. Again, simply let y equal 0. So we have 0 is equal to negative log base 2 of 2x plus 6. Okay. So after rearranging everything into exponential form, we have 2 to the 0 power is equal to x plus 6, which means, of course, 1 is equal to 2x plus 6. And then negative 5, is equal to 2x. So the x-intercept would be negative 5 over 2, or of course negative 2.5, which is what we have on our graph right here. Next is the y-intercept. So let's go ahead and find that as well. So this is where we let x equal 0 and solve for y. 2 times 0 plus 6. Now, unfortunately, this simplifies to y is equal to negative log base 2 of 6, which, of course, 6 is not a power of 2, so this doesn't evaluate quite as easily. We will use our calculator to estimate a value, so we can rewrite this as negative log 6 over log 2 using the common logarithm, and we'll get an approximate value of negative 2.585 and so forth. So, which means this graph is probably supposed to be a little bit less steep, the curve, so somewhere around here. Okay, so those are the examples where we applied transformations to logarithmic functions and plotted them. Next, we are going to be given some functions, and we just need to describe what the transformations are. And similar to the last unit with exponential functions, we're going to isolate the transformations that affect the y variable on one side and then the x variable on the other. Okay, so this is how it's going to look like. So subtract 2 from both sides in this example 3a. And inside the parentheses, we can factor out the 3. So like this. And then we can multiply both sides by negative 1. So we have negative y minus 2 on the left-hand side, like so. And on the right-hand side, we have log base 5. And then 3 times x minus 12. So now we can describe the transformations. There are 4 in total. The 2 that affect the y variable are a reflection over the x-axis, and that the graph moves up 2 spaces. The 2 that affect the x variable, one is a horizontal stretch by 1/3, of course, and 12 spaces to the right. Okay, so similar with example 3b, we'll multiply both sides by 4, so we have 4 and then y plus 7 is equal to log base 5, and here we're going to factor out a -1, so we can rewrite 6 minus x as negative x minus 6. So it's easier to figure out what the transformations are this way. So with the y variable, we have a vertical stretch by a factor of 1/4. And the graph, of course, moves down 7 spaces. And then with the x variable, we have a reflection over the y-axis. Follow that up with a translation 6 spaces to the right. Okay. From there, we could use the table of values for y equals to log base 5 of x, and then transform that table of value using the transformations listed, and we can graph the graphs just like we did in the previous 2 examples. Okay, let's move on to example 4, slightly different kind of question. So here we're going to be given 2 graphs. The red graph is a transformation of the blue graph. We are going to determine the equation for each red graph. So one way of doing this is to list out some key points on the original graph. So here we have 1, 0, and of course 2, 1, 4, 2, and 8, 3. So of course the function is y equals to log base 2 of x, which we graphed earlier. And we're going to compare points on the red graph. So here we have, instead of 1, 0, we have 1, 2. Instead of 2, 1, we have 2, 3. Instead of 4, 2, we have 4, 4. And finally, instead of 8, 3, we have 8, 5. So simply put, then the y values simply increase by 2. So the red graph is a transformation up 2 spaces, and therefore the equation is just simply y is equal to log base 2 of x plus 2. And that's certainly a very good way of interpreting what happens. However, there's a different way of thinking about what the transformation was, and we'll be looking at that in more detail in the next section once we cover the laws of logarithms. But for now, consider the points here 1, 2, and 4, 2, and also 2, 3, and 8, 3. Instead of thinking about how the points were moved up 2 spaces, we can see that the point 4, 2 becomes the point 1, 2, or we could interpret it that way. And that the point 8, 3 becomes the point 2, 3. If that's the transformation, then it's actually a horizontal stretch by 1/4. Okay. Just gonna go add that in. And if that's the case, we actually have the equation y is equal to log base 2 of 4x. In the next section, we're going to show that these two, y equals to log base 2 of x plus 2 and y equals to log base 2 of 4x, are actually the same thing. Okay? In fact, there's a third way to write this equation, and that is up 1, or sorry, it will be a horizontal stretch by 1/2 and up 1. And that is also possible. We'll get y is equal to log base 2 of 2x plus 1. Okay. And so just as how exponent had exponent laws, logarithm also have laws of logarithms that we can use, so rules that we can use to rewrite certain things. So a consequence of that is that these three are all valid equations for the red graph. Okay. Let's move on to the next part here. We have y equals log base 4 of x and then the red graph. So here, one way of thinking about it is just log base 4 of x and then plus 1. But we could also think about this as y equals to log base 4 of 4x. Okay. So finally, it's going to look at inverse of functions. Now that we know the exponential function and the logarithmic functions are inverse of one another, so we can go ahead and use algebra to determine inverse. Let's go to the first one. Here we will rewrite this as x is equal to 2 to the y minus 1 power plus 3. We start by switching x and y. And now we're going to solve for y. So we're going to subtract both sides by 3. And now we can rewrite this in logarithmic form. So log base 2, of course. And then the argument is going to be x minus 3. And that's going to be equal to the exponent on the right-hand side, y minus 1. And to finish solving for y, we can write this as y equals to log base 2 of x minus 3 plus 1. Okay. One more. So again, we start with switching x and y. So we have x equals to log base 5 of y plus 1 minus 3. We're going to add 3 to both sides. And then rewrite this as in exponential form. So we have 5 to the x plus 3 power is equal to y plus 1, which of course means that y is equal to 5 to the x plus 3 power minus 1. And that's it. So that's it for today. We looked at the logarithmic function and its transformations. Once again, thank you for listening.